Alright, so Gen Chem 2 here at Dalton State, we usually start with the empirical gas laws. So we'll jump right into that. Some places that's back in Gen Chem 1. We're following this new textbook here. So gases, common gases in chemistry. I take some exception to that idea because we're going to talk about just coming up in our next unit. We're going to talk about how everything, almost everything. There are some things that will decompose before they get to a gas phase, but how most everything can get to a gas phase. So I would note that the table here in your book doesn't even include water, and obviously it becomes a gas pretty easily. So also remember from Gen Chem 1, you should know about diatomic gases and monatomic. Sometimes you have, your monatomic gases are usually your noble gases, so they have full Lewis structures already, but your diatomics need something in order to. They have either 7 or some other number of valencies, so that they want to combine. So remind yourself of those if you need to. So if you see so many moles of hydrogen gas, just make sure you understand that that's H2. So 1 mole of hydrogen gas contains 2 moles of hydrogen atoms, just in case that comes up. You could also have other heteroatomic compounds as gases. You're probably familiar with the typical 4 states of matter, or at least 3, solid, liquid, and gas. The most common 4th will be plasma. We're going to talk about those in the next section. The reason we start with gases, like I said, they're often treated in Gen Chem 1, but they allow us to get into things and start doing labs and start doing things with mathing with the gas phase relationships. So they give us a kind of a quick start to the course. So the idea is that gases are, at least of the solid liquid gas, they're easily compressible, and they can change volume and shape pretty easily. And so that gives us a way to experiment with them and look at the properties there. So physical characteristics of gases is that they do assume the volume and the shape of whatever container that they are contained in, and that could be a closed flask, it could be a room, it could be an atmosphere of a planet. They're going to assume that volume and shape of what they're contained in. They're also the most, at least modifying your book here, most compressible state of matter, at least of the solid, liquid, and gas trio. They're really not, they're not necessarily more compressible than the plasma or some of the other exotic phases. They do mix evenly and completely when you put them in the container together. And almost universally, they'll have a significantly lower density than either a solid or a liquid. So your condensed phases, usually you can physically separate them just by letting them settle to the bottom of something. A little bit of physics to get us started. We need to talk about what pressure means. Now, pressure is related to force, but it is force divided by your area. Give you an example of this. So I apply less downward force in form of weight than, let's say, my Jeep. But I could walk across a bit of mud and sink in it more dramatically than my Jeep will. Even though the Jeep weighs more than I do, it spreads that weight, that force, over a wider surface area. And so the actual pressure exerted on the mud is less than the pressure that I do walking along. And so that's why that works. So force, of course, is mass times acceleration. Again, that's a physics thing. If we need to delve, I don't want to spend too much of our chemistry time talking about the physics of it. But if that's not accessible to you, I want to fix it. So come and let me know if we need to talk through the basics of the force, acceleration, mass type stuff. Units. All right, so units of pressure. You're going to get several different ones, and what this depends on mostly is preferences of the community that are doing a certain measurement or calculation. So in physics, we tend to use a pressure unit called the Pascal, and the reason for that is for calculations, 1 Pascal is precisely 1 Newton, that's a force unit, divided by 1 square meter, that's your area unit. So 1 Pascal works out nice mathematically that it is 1 Newton per square meter. But if you are looking at atmospheric pressure, which most of the time a lab will be at essentially 1 atmosphere of pressure, that's the pressure that you're probably feeling right now, sitting somewhere near the surface of the Earth at typical latitudes. You'll feel about 1 atmosphere pressure. That's the pressure that the atmosphere above you is pushing down on you with, divided by a unit surface area. So 1 atmosphere. The older version of this same situation is 760 millimeters of mercury. So if you hear somebody say about the mercury going up or down, that's what they're talking about, the pressure actually. 760 torr is the same measurement as millimeters of mercury. 1 atmosphere, though, and this is why we don't use the physics ones, because if you're always working in atmospheric pressure, you could always have to use this 101.325 kPa. Well, that's kind of, or you could just say, well, let's just define that as 1 atmosphere. That's what we do usually in chemistry. Now, we might also say, well, 101,000. What if we did 100,000? And that's a unit also. It's called 1 bar. So 1 bar is defined as precisely 100,000 pascals of pressure. So you see that these are unfortunately close to each other. Now, for purposes of your cheat sheet, like if I were setting up my cheat sheet, I would have all these on it. To be honest, if I write a question, it's probably going to be in atmospheres. But here's the thing. I write questions for you, and I also steal questions from quite a few other sources. Well, those stolen questions might be in atmospheres, but they might be in bars. They might be in pascals. They might even be in millimeters of mercury or torr. So I would probably put all of these on my cheat sheet just in case. All right, so we're talking about empirical gas laws. I wanted to reinforce, remind the idea of law versus theory. Just remember that these are kind of different things. So it is incorrect to think that like a theory could ever become a law. That's not how that works. They're different things. A law simply tries to explain mathematical relationship. If you do this, this happens. A theory then seeks to explain why that happens. So they're really not the same thing at all. So the empirical here just means, well, here's the experiment and it's what it says. We don't know why. That's what happens. So the empirical gas laws are like, well, here's the mathematical relationship. We've done it over and over again. Here's what's going to happen when you heat the gas up or you compress it or whatever. Then we'll talk later about kinetic molecular theory. That's a theory that tries to explain why the gases behave this way. So the first of these gas laws is Charles's law. This is the idea that variation of gas volume with changing temperature but maintaining constant pressure is directly proportional. What that means is that you can graph it and it's linear. So linear, don't be confused by linear now. Linear doesn't mean that it has to have a slope of 1 to 1. Often it does not have. It just means that it has to have some consistent slope. All right? So you have, as you increase temperature, you increase volume, given that you have a constant pressure. So we could also say it this way, that volume is proportional to, that's that little symbol there, is proportional to temperature. Same thing, is if you increase one, the other increases. Now, proportionality doesn't say equal here, because often you have to have some constant. Now we can change our proportional to equals by saying volume is equal to some constant, and that's going to be the slope of this line, some constant times the temperature. So usually, though, you'll see it this way. V1 over T1 equals V2 over T2. Remember that it must be in Kelvin. So remind yourself how to convert from, to go from C to K is just add 273.15. To go from K to C is just subtract 273.15. So practice problem, just to look at how it works. So what do we have here? Well, so our sample of oxygen at a given volume and temperature and pressure, let's see, what volume is it going to occupy? Oh, we have a new temperature here, but the problem says at the same pressure. So my pressure is going to stay 10 atmospheres, so it's really not going to be part of my maths here. Oh, well, that means I can just use Charles's law. Now, interestingly, my temperature goes from 30 to 60. Now, if I were putting this problem in front of you on the board in a live class, I'm going to say, well, look, 30 to 60, does it just double the volume? And why? And it's going to be a trick question because no, it doesn't, right? This is an example of why it is drastically important here to convert to Kelvin, right? Because if you do that, well, we have 303.15 K and 333.15 K. Oh, wait, we did not double the temperature. We went up by 30 K, but because we started at 303 K, we didn't double it at all. And so that's a big trick and an example of why it has to be in Kelvin. So, but here we do have a volume and a temperature, a new volume and a new temperature. We want to know what the new volume is. I would set the new volume as V2. It actually doesn't matter. Either one can be V1 or V2. Just you have to keep the 123.4 with the 303K and the V2, the unknown, with the 333K. So I tend to rearrange these before I plug in my values, but that's okay. Either way works. I think it's a lot more writing here to do it, to plug it in first, but I just wanted to show where everything goes in the formula. And then you just algebra it through. So you got multiplying on top. So I've multiplied both sides by T2 here. Which actually probably, here, let me just write what I did there to make sure we're on the same page. So basically what this is, it is V1 times T2 over T1 equals V2. And what I've done here is I've just multiplied both sides by T2 to isolate my unknown here, right? If the algebra is going to give you fits, make sure you come talk to me and or the math lab. Probably both is the best idea, just to make sure that we get you caught up on the algebra. At this point, this probably should be no struggle for you whatsoever. Also, notice here what happens to my units, right? So I kept my K here when I multiplied, right? So there's that T2 that I'm multiplying both sides by, right? Well, look at that. The K's are going to cancel nicely, leaving me milliliters, which is what I wanted in the first place. And so V2 is 136 mils. Remind yourself on sig figs why this needs to be 3 sig figs and not 4 here. Just make sure that's clear to you. If not, come talk to me about a review of sig figs. All right, Guy-Lussac law. So this is variation of gas with temperature. So gas pressure and temperature, but now this time instead of holding pressure constant, this time we're going to hold volume constant. So we're going to lock it in some flask that cannot change volume, and we're going to heat it or cool it. So what's going to happen then? Well, so it can't change volume, so it's going to change pressure instead. So also proportional. So you can see it this way. This is most common, P1 over T1 equals P2 over T2. You could also graph it and say that pressure is proportional to temperature. You'll still have that same graph, that linear graph that we had in the Charles's law, constant times temperature. Mostly you see it as P1 over T1, P2 over T2. And again, it has to be in kelvins. Let's do a practice. Sample of oxygen again, all right, same thing, 543.2 mils, 30 C, 1.123 atmospheres. But this time we're going to say, what is the pressure in atmospheres if the temp is increased to 125 C and we somehow hold the volume constant? All right, well, here's our relationship. And we're going to say, well, let's plug in there our knowns and unknowns, right? So look at what I've done. So because my volume is constant, right? It's nowhere in here. There's no volume in my relationship. So I just take my 1.123 atmospheres and my 30 C, and then my new temperature, 125 C, much warmer here, right? And so you get 100 and get this out of the way here. You get 1.123 atmospheres, 398 K. They're going to cancel again. Why did that not cancel for me? Go cancel that. This cancels this. So see, your K's cancel again, leaving atmospheres as my units. So 1.47 atmospheres. All right, so why is this one 3.6? This is a trickier one, slightly trickier. Now, if you take the shortcut of just looking for the least sigs in the problem, there they are, and that is the real reason why it's at 3 sigs. This is really only 3 sigs down here is the problem. So remind yourself on the sigs, they still do matter. All right, third one, Boyle's law. All right, let's see. Charles's law, we held pressure constant, right? All right, Gay-Lussac, we held volume constant. Well, let's do it the other way around and hold our temperature constant. It's actually kind of hard to do to actually hold the temperature constant. There are ways to try to do it, like holding stuff in a water bath and stuff like that. But this just says that if you can do that, then you can make a new relationship. But it gets a little weird this time, right? Because it's no longer that simple proportionality. You see that these are different now. It's not P1 over V1, it's P1 times V1. This one's different. So pressure is inversely proportional to volume. So that means if you increase pressure, you decrease volume. And that should make a little sense to you. If you have something in your hand and you squeeze it, you decrease its volume, not increase its volume. So some constant times 1 over volume. Now, if you look at a graph of that, here's what it looks like. So we're going to get a lot into trying to linearize stuff, especially when we get to the kinetics piece. So it's a good preview in this area. So if you think about your mathematical functions from 9th grade algebra, there were several different ones that you needed to know. You needed to know what a linear function looked like. You needed to know what a quadratic or an x squared function looks like, maybe a cubic function, exponentials, and this one is another one that you should have been encountered there, y equals 1 over x function. So that's your inverse function. And it has this curve to it. So we might try to set up our graph in order to what's called linearize this. So instead of plotting, here I've plotted pressure versus volume. Instead, I might plot 1 over pressure. So take my pressure readings and take the reciprocal of them so that I can plot them. And oh, lo and behold, now I have a nice y equals mx plus b, and that'll be easier to do the math of. Oh, there, I've written it nice and clean here. Let me get rid of that. So that way, the reason for that is so that we can work on the maths of them more easily without having to get into the more complex workings. We're trying to avoid calculus for y'all as much as possible, since it's not a prerequisite for this course. It does make it easier if you've had calculus, but it's not a prereq, and so we're trying to make it so that everything comes out in nice linear terms whenever possible. All right, nice straightforward practice problem here. We've got our setup again. 123.4 mils, 30C, 1.123 atmospheres. New pressure, so I need a new pressure in atmospheres if the volume is decreased and the temperature is held constant. Now, note here, this is not a realistic situation for engineers out there. It's pretty difficult to hold. If you decrease volume this drastically, it would be really, really hard to hold the temperature constant. But let's say for the hypothetical world of the problem that we could do so. Our relationship is going to be P1V1 equals P2V2. Well, there's what we've got. We can rearrange that algebraically by dividing both sides by 12.3 mils to solve for V2. 11.3 atmospheres of pressure. That 11.3 atmospheres may not sound like a whole lot, but that's a pretty drastic increase in pressure. Most vessels are not going to handle that kind of increase in pressure, probably. Okay, so all three of those different things have their different relationships, and they look kind of similar, right? So what, we could just kind of staple all of those together, right? So you've got, let's see here, let me see my highlighter. You've got that P1 over T1, yeah. But you've got that V1 over T1. But then you've also got that that P1 times V1 relationship. And so, yeah, this actually does work to put them all together like this. So P1 V1 over T1 equals P2 V2 over T2. So this is a good one to use when you've got multiple things changing in the problem. So maybe similar to the last problem, except that temperature is not held constant, or if you have two things changing, that you've got a relationship here. As long as only one of these things is unknown, you could solve for pressure, you could solve for volume, or of course you could solve for temperature, but you only have one equation here, therefore you can only solve for one unknown. So I put a note in here about balloon problems. They're tricky sometimes to look at your balloons in the problem and try to decide, well, wait, is my balloon going to be is it just going to be able to expand as much as it wants to. If it can, then say, well, okay, then we're going to call it at 1 atmosphere of pressure or whatever the surrounding pressure is. Sometimes we'll compress a balloon. Just you have to. That's kind of a reading skill. Read the problem and try to figure out what it's trying to set up. All right, so let's think about these now. What could cause problems for the gas laws? So those gas laws are set up so you have a closed system and nothing really going on in the system except for the variables that are talked about: the temperature, the pressure, and the volume. Those are the only things that can change, and that still work. So if you were to change the amount of gas, all bets are off. If you generate gas or you consume gas or you somehow react gases together so you form a different amount of gas, well now P1 V1 over T1 equals P2 V2 over T2 does not work. If you condense or something like that, then it doesn't work. If you change phases, if you have a chemical reaction so that the different gases, they might or might not have the same stoichiometric ratio, so you got to figure all that out too. All right, so if we're going to run into all of these potential problems, then what do we do about it? We use this. It's called the ideal gas law. All right. For an ideal gas, we'll talk about what that means. We can always have this relationship right here. Okay, so my pressure, right, is, let's change this to a laser pointer here. So this is my pressure. That's the gas pressure. The V is going to be my gas volume. T is the temperature. All right, those three are the ones we've been dealing with. But here's where it changes. Now, that first problem that we could run into is changing amount of gas. Well, the amount is the number of moles. So, right? So the number of moles of the gas right here is moles. And then we have this R, this big capital R. This is the gas constant. Okay? So that's the real trick that makes this thing work, because the gas constant is the same everywhere, every when in the universe. There's actually some speculation that in maybe the first few microseconds of the universe, there might have been a slight variation in R, but certainly not since then. And it would change everything that you know if R were to change. So it is just this super static constant of the universe. Well, so if that's always true, you can always solve for R, and so you can use that to make a mathematical relationship that just works. So a problem that we run into is there are different values for R. Now, I just said that R is constant throughout the universe. Sometimes this confuses my students when I say, okay, R is constant and there are different values, but really the only reason there are different values is because we're using different units. These are really the same value, just expressed differently, because this first one, 8.314, is in Pascal meter cube per K per mole. And the second one, joules per K mole. Now they work out the same, and that's because of the 1-to-1 Pascal joule definition. But then if we've got bar going on, right, well, that changes everything. It moves the decimal 3 places. Okay. Or, if we've got calories, we hardly ever use that anymore, but if you were to, that changes it to this guy. If we're working in atmospheres, it changes it again. So these are really the same thing. They're just expressed differently with these units. I've given you a link here for, this is NIST government website for define all the things. They're really great about that. They just put everything out there. Now, It's a little hard to get through it, to kind of wade through it sometimes. But if you really, really need a number, here's the official values. That's a place to go to get them. So if we've got this PV equals nRT that's going to work, now we're down to just algebra to try to solve a problem, right? So it's more powerful even than that combined gas law, because now you can just use it to solve for any single unknown. And like I said, the trick is that you can solve this equation. So if you start it, right, you can solve for R. PV over NT is equal to R. And then if you change your conditions in your reaction or whatever you're doing, PV over NT is still going to be equal to R. It's just that you've got a new situation. So your starting pressure times volume divided by number of moles times temperature, well, that's equal to R. And your final pressure volume over moles temperature is still equal to R. So now, see, the moles is involved, kind of like the combined gas law, but now it's got moles down here, and that's going to solve almost all the problems. And to be honest with you, I don't use the combined gas law. I just use this. And because it's fewer things for me to memorize, I don't use Boyle's law and stuff like that. I just use the ideal law, because the ideal gas law is going to work for more things. Kind of a instead of having a bunch of different tools, it's kind of your hammer screwdriver. One tool in the toolbox that does almost all the things. Now, it is almost all the things. My chemistry majors need to pay attention to this. For everybody else, unless you're maybe some of the chemical related engineering majors, certainly Chemi, but maybe like aerospace engineering, this would probably be important, something like that. But my chemistry majors, it's going to be important for you in a course called physical chemistry. So the idea of the ideal gas law is that gases act ideal. Well, they don't always. So we'll talk later about what the what's going on with the assumptions in the ideal gas law, but it does get more complex when you have to correct for, oh, wait a minute, my gas molecules are actually attracting or repelling each other. Okay, now I've got to add a new term in. So it's not just pressure, it's pressure plus a correction, which is related to the volume. Okay, and then, oh, wait a minute, what if I have really, really big molecules? So a hydrogen molecule or an oxygen molecule or a water molecule, those are tiny. They are almost zero space, right? But now if we've got something like, this came up a lot here recently, virus particles. Well, virus particles are actually quite big. So now if we're going to use ideal gas law, can't use it. It's not ideal because the volume of those molecules is actually significant. So we have to put in a new correction. So our V term has to become V minus a correction factor for the volume molecules. And this is just the first step. There are actually multiple steps to this. It can get even more complicated than this. I just wanted to give my chem majors and maybe some of my engineers kind of a preview of what might be coming in the future. All right, so that'll end us up on that. So next will be video lecture 2. We'll talk about stoichiometry. So what we're going to do is we're going to start talking about when that N is changing, when the moles are changing, and what's going on with that, and other things that we can calculate, like diffusion and stuff like that. Read through your sections 9.3 to 9.5 for this next one, and expect in class we'll be doing a lot of these gas laws practice problems. See you there.